Hey class, this is a quick introduction into hashing, hash tables, and basically what they are. Now, so far at this point, we've covered linked lists, we've covered arrays, we've covered stacks and queues, various other ways to store data. Some are more efficient than others, trees. Uh, if we're searching for something, in a tree, for example, we basically cut the tree in half every time we move down one level. Which means finding stuff in a tree is much more efficient than finding it in an array. Now, a hash table is also, if built correctly, super efficient. And let me explain what it basically is here. We start off with an array, just your basic array. Now, if I want to store something in this array, let's say the name Bob or something. Uh, Bob. There it is. I want Bob to go into this array. Boop. There we go. Maybe. Now, once I have Bob ready to go, I run what's called a hash function or hash key. The hash function is going to take Bob and transform it using the key into a number in this array. So if we want to use a really stupid simple one, what if we just added up the ASCII values of the letters? You know, this is worth this is worth that, this is worth this, and we just add them up. Let's just say, for argument's sake, since I only have 10 slots here, that Bob, capital B, capital O, capital B, hashes out to be 6. Well, let me make this a little smaller. Go. So what I do is I decide I'm going to move this. If I can get this. No. Let's try this again. I got to act all different every time. There we go. So Bob goes into 6. Now, Jim or Amy or whatever, you add those ASCII values and they hash out to a different location. And it plugs it there. Now, in this example, because we're using ASCII values, the only way they would hash to the same place, which is possible, is if the letters in it was exactly the same. So if we're hashing, Bob, well, you'd have to have Bob to go to that same place. Any other set of letters would put you somewhere else. Now that's super efficient because if it's done right, everything will hash to different locations. Let's say I had a size million array, and I just hash it, plug it in. Now, if I want to look for something, I don't have to go through the entire array. I just run the word through the hash function. It tells me what number, what location it is, and I go directly to 6 and go get Bob. So hashing is actually one of those things that's really, really quick. If I want to find something or put it in, way faster than arrays, even faster than trees and other things like that. And it's used a fair bit, depending on what data structure, what information you're trying to use. Now, it does have problems, of course, like any data structure. One, if I hash something to the same area. So if I hash and they end up hashing to that same location, what do I do? Well, the simplest way was say BBO, since my hash function revolves around the ASCII letters and what they're worth, would hash to the exact same location as this. Probably didn't make it big enough. There we go. Come on. There we go. So BBO hashes to 6 as well because the letters are the same. Well, now it looks like RRO, but let's back it up a little bit more. Doot. There we go. Now, because there's something already there, we have what's called a collision, meaning this is supposed to go in there, but there's something already there. And that's a simple, I hash it, I get the function. Is that place already occupied? If it is, well, that can't go there too. There's two ways you could approach fixing that. One would be, well, that's got something in it. Let's go to the next one and just plug it down there. Now the problem with that is, when I'm looking for something, I'll look for it here. It's not there. Then what would I have to do? Just check until I found a blank for the next one. Wouldn't exactly be the most efficient way to do things. Uh, the other way I could do this is, instead of using arrays, I could use an array list, which means if something collides, well, I just make a little linked list here, and I move my item into that list. So this thing will be basically have a next that points to the next item in the list. So if something collides, I just simply have to say, well, dot next is going to be the new thing. Dot next is going to be the new thing. And that's probably the most efficient, elegant way to do that. So if I'm looking for something, is it there? Nope. Is there a next that's not null? Yep, let's check that. Is that it? Yep, there it is. Or nope, is there a next that's not null? And if there is a null, well, it's not there. So there is a couple of different ways we can go about doing this, and I think this is probably one of the better ones, rather than just dropping it to the next slot. And this is roughly kind of how your basics of hash tables work. I just have a big array, and now the hash function, like I said, can be some pretty complicated math depending on what you're doing. But for us, for what we're going to do for our example in class, we're just going to use words and the ASCII values. It makes it pretty simple, really simple actually, but you'll still kind of get the effect or the idea of how it works. If we timed it uh, using all the big O notation or whatever, hash tables would statistically be faster in most cases. Now this is your quick introduction into hash tables.